Swayam Prabha. Digital India. Educated India.
Hello students, welcome to our next module on optimization in decision making as part of our course on infrastructure systems, decision, risk and resilience. In this particular module, we are going to move ahead from our discussions on probability and statistics as applied to various infrastructure problems to a new concept of optimization in infrastructure. We will begin with univariate optimization, multivariate optimization, discuss how convexity of function is decided and why it is important, and as always we will also look into some examples that how these particular concepts are applied to both problems mathematical in nature as well as applied in nature. We already mentioned about this briefly when we were talking about probability and statistics, that we are doing all these particular exercises to arrive at a decision. Now, if you have to arrive at a decision, you would expect your decision should be optimal. Optimality here should mean that with available resources or constraints, it should maximize the profits or minimize the costs. It should maximize the greater good of public if it is a public project, while still ensuring that we are not violating the constraints that we have on resources. Because when we talk about any engineering problem, we are always going to deal with finite resources. These resources could be in terms of land, these could be in terms of revenue, it could be in terms of human resources available to execute certain tasks. So, although we would always want our gains to be infinity and theoretically speaking our costs to be minus infinity, we realistically will never achieve that, because we are working under certain sets of constraints that have to be abided by. Now, just knowing this conceptually is important, but certainly not sufficient for engineers, because engineers have to arrive at quantitative decision making, come up with a numerical or quantifiable justification of whatever decision that we have taken is optimal within certain framework. And that is exactly what we are going to discuss as part of this particular module, that how to write all these objectives that we want to maximize or minimize as mathematical equations, bringing the constraints that would be binding on these particular objective functions, and still arrive at a decision which we would say is optimal. It could be maximum or minimum depending upon a particular situation that we are talking about. So, a few examples of optimization in infrastructure systems include that we would like to do some cost minimization in construction project. For example, if engineer is designing a bridge or a dam, they would not go for designing a bridge of titanium, or they would not design a dam of infinite height, because the costs are disproportionately proportional to choice of material or construction height or material that we are going to use either in dam or bridge, and hence cost minimization is always a big consideration while planning and executing the engineering projects. Then another role of optimization is risk management. As we learned in our probability discussions, that we would always try to minimize risks. We also realize that reducing risk to zero is practically impossible, because we would be dealing with various choices, and these choices would again be constrained either by their technical feasibility, or we would have limited choice or options because of the budgets that are being available. But still, as researchers, as scientists, as policymakers and practitioners, we always want to minimize our risk, be it designing the flood defenses or disaster mitigation. If we are proactively or reactively taking certain adaptation measures, we would like to see their impact for much longer period of time. And when we want to see their impact for longer period of time, we are essentially trying to minimize risk over a period that is under consideration. Then coming next to transportation networks and energy grids, we would also want to minimize resource allocation. There is a burst of many companies that these days deal with supply chains. They would want to minimize the inventory, they would like to minimize the inventory related costs, overheads, because if you produce certain product and there is limited to no demand in the market, you would still need warehouses to store those particular locations at certain locations. Now, if you have to store all those goods at a particular location, you are going to incur the costs. Then also what may happen is that you have created certain warehouses or storage facilities in certain part of the country, but demand is originating in altogether different part of the world. Then again you are going to incur the transportation and logistics related costs. So, again any logistic planner would want to minimize the transportation and logistics related costs while designing these particular networks, or for that matter any supply chain related network, so that the overheads could be minimized while sustaining or maintaining the profits or margins. Similarly, examples extend to other network systems, for example, water supply systems. We would like to minimize the costs, we would also like to minimize the head losses that are taking place in the system. We would also want to have a material of pipes that should last for longer duration of time. It may happen that we may invest in a cheap piping material, but it may get corroded or may start leaking in well within its intended life of service, and then it is going to be a recurrent maintenance costs. So, we would like to have an improved efficiency in water supply systems, and overall when all of these are put together, we are essentially also looking for optimal design for urban infrastructures to handle various environmental stresses that these systems are going to face. So, for example, flooding is one burning example. Every part of the city in most of the metropolis areas, they suffer from this persistent issues of flooding. Now, as planners and stakeholders plan to invest to minimize the footprints of flood, certain investments have to be made. So, all these investments would have the optimality over certain period of time at its center when all these plans are consideration for optimization in these infrastructure systems. Again, going back to one of the examples that we already discussed earlier, was this classic cofferdam problem in probability and statistics, where I mentioned that I will revisit this particular problem again as and when we will talk about optimization. But after learning probability and statistics, I hope that you would have much more familiarity with the terminology involved in this particular problem. But let us try to look into the problem from scratch and see that how far we can go, and does this problem give us a right motivation to step into the concepts of optimization as applied to infrastructure problems. So, here a quick recap of the question. Problem is that an engineer is assigned to determine the optimal height h of the cofferdam to adapt to flood risks. The flood depth follows an exponential distribution and frequency follows a Poisson distribution. If you recall, Poisson distribution was a discrete distribution, whereas exponential distribution was a continuous distribution, and it makes sense because number of floods that you can have in a given year could be 1, 2, 3, 4 and so on. It has to be discrete, whereas exponential distribution flood levels can take any value 0, 1.1, 1.2, 1.3 meters and so on. Also, we are given certain parameters of these particular distribution. For example, it is specified that mean flood occurrence rate is 1.5 floods per year, mean flood depth is 5 feet above normal water level. Also, we are given expected loss each time coffer dam is overtopped, and design life of coffer dam is given as 2 years. Again, a quick recap: coffer dams are typically typical structures that we provide whenever certain work has to be done within the water bodies. For example, if a bridge pier has to be built in the river, then what we would do, we would create an isolated island which would have no or limited amount of water entering into that, and this is typically done through a hardware intervention where sheet piles are installed, followed by certain superstructure, and that superstructure is watertight, so that water would not enter into the coffer dam where the work is planned to be conducted, because there would be manpower, there would be machinery in that particular area that we cannot afford to be underwater if and when flood level rises. Also, you can also imagine that we cannot have an infinite height coffer dam, because it would cost material, money and manpower. So, typical 3 M's that civil engineers often associate with, we have to always manage them with constraints around them. Good thing here is that we are not specified any constraints. So, this would be a bit easier problem to solve from optimization side. So, we know the cost function. Cost function is that C naught plus 3000 H plus risk of overtopping. So, C naught is clear, that does not matter you are building a coffer dam of 1 meter or 2 meter or 3 meter, you still have to do some basic investment in installing the sheet piles or making the foundational work. As H increases, cost is increasing linearly. Again, this is an assumption or best of the data that is available to us. So, we are doing the prior analysis and not the terminal analysis here. So, we assumed certain form of this cost function plus some risk involved, that because of overtopping, how much would be the cost that we have to incur. Now, intuitively we may be very much excited to say, okay, risk should be 25,000, but as we learned that risk is not simply the monetary value, but it is monetary value multiplied by probability of loss happening, and this probability of loss happening is not necessarily 1. So, we have to calculate what is the probability that we will incur this $25,000 loss in the design period, which is given to us as 2 years. So, if we look into this particular solution, so again, since we have already dealt with this particular problem, we may not do math from the scratch, but it is a quick recap that we can model number of floods as Poisson distribution, where we learned that probability of x, where x is random variable, in Poisson can be given by e raised to power minus lambda 1 to the power x upon x factorial, and this lambda is the parameter or mean occurrence rate per year, which is given as 1.5 floods per year is the expected number of floods multiplied by total design life of a particular infrastructure system. In this case, we know that this design life is 2 years. So, our lambda 1 comes out to be 1.5 times 2, which is equal to 3. Similarly, depth of flood that I have highlighted in red is given to be exponentially distributed, and we know that exponential distribution is also characterized by a parameter. It is a single parameter distribution given by lambda 2 e raised to power minus lambda 2 times x, and lambda 2 is 1 divided by average depth. So, that is the value of parameter it would assume. We were given that the average depth of flood water is 5 feet. So, in that case lambda 2 becomes 1 by 5 by definition of this particular parameter, in a sense that this would come out to be the best estimate. We already looked into example of maximum likelihood estimate and tried to relate it to moments of these particular distribution. So, in case of exponential distribution, lambda 2 comes out to be 1 by mu. Now, there are two considerations that we have to pay attention to. We can, every time flood will happen, water will enter into coffer dam, there would be losses, and we really do not know how many floods will happen. We can have 0 flood, and theoretically we can also have infinite floods. However, there zero floods will have certain probabilities of occurring, so would infinite floods would have some probability of occurring. So, we have to account for entire spectrum of 0 to infinite floods possible, and for each flood, whenever flood happens, we would also have variations in the flood depth, because that is also a random variable in our case. So, first of all, what we will do is that we will find what is the probability of overtopping in each flood. Now, if you have already built a coffer dam up to height h, that means if water level is below h, let us say h minus 1, h minus 2, h minus 3, that means water is not going to enter into coffer dam at that particular point, as a result of which we would not be worried about water levels below height h. So, overtopping will only happen if flood height is from h to infinity, and since flood depths follow the exponential distribution, what we would do, we would integrate this particular expression of Px from h to infinity, and when we solved this earlier also, we got this as e raised to power minus h by 5. This is a small piece that I am leaving as a homework. You can refer to earlier slides or try it yourself. This is a straightforward integration. In this particular case, you would get an answer as e raised to power minus h by 5. In this case, x is h, because that is the random variable in case of flood. In case of number of floods, this x is actually number of floods, that is 1, 2, 3 and so on. I use the same notation for a reason, because when we specify probability distribution function or probability mass function, you would see that they would both use same notation for different variables, but we have to really understand that what is the physical context of that particular random variable. For example, flood in one case and its height, and in another case number of floods being happening. Now, this was the condition that what is the probability of overtopping for each flood. But we have to also see what is the overall probability of overtopping over 2 years of period of time. Now, as I mentioned, that number of floods can be 0 to infinity. This was for one flood. Then for I floods, we have to multiply this by I, but we do not know how many floods will happen, because that is also a probabilistic event. So, what are the chances that we will have I number of floods in the design period, which is again 2 years in this particular case. So, if you see here, it becomes I into Pi, and I is summed from 0 to infinity. If you pay attention to this I into Pi, it is nothing but expectation of I, and we know that I is following the Poisson distribution. If you know that I is following the Poisson distribution and this term is free of h, free of I, it does not have any reference to I. So, this particular summation simply becomes e raised to power minus h by 5 into 3, that is 1.5 into 2 by the mean estimate of Poisson distribution is the parameter itself. So, the total loss comes out to be 75,000 e raised to power minus h by 5. Now, when we talk about the total cost in this case was C naught plus 3000 h plus 75,000 e raised to power minus h by 5. And now, this is what we have to account for when we do any minimization and so on. So, now if we pay attention to this particular equation, and this is where our optimization discussions start. An engineer would be tempted to build a coffer dam of a very large height, so that risk is minimized. So, and that is also clear in this particular equation, that is if you have h to be a very large value, e raised to power minus x, where x is a very large value, would be a very small number, and hence your risk will drop down. However, problem lies in this particular term, where you have a term of 3000 h, but this h will increase linearly as height is increasing. So, while increasing height will reduce the risk, the direct costs will increase in a linear proportion. In some cases, you may have this particular function as 3000 h square or h cube or even some other nonlinear function of h. So, we have to identify a sweet spot where there is a balance between the direct costs that we are making versus risk that we are averting, and that sweet spot is going to be our optimal solution. We have already learned this in our high schools and senior secondary schools, that if you have any function f of x and if somebody asks you to find the maxima or minima, we are used to say that differentiate it with respect to x, equate it to 0, whatever are the roots of this particular equation, that is going to be the solution. So, here we would get away with that if we differentiate it with that particular h, that is total cost differentiated with respect to h and equate it to 0, we would get the optimal value of height, which in this case comes out to be something around 8 feet. But the broader question arises, how do we know that this is indeed minima or maxima with this information? So far we are used to deal with what we call as necessary conditions. This h equal to 8.05 feet is an outcome of necessary condition for point to qualify as minima or maxima, but this necessary condition does not guarantee that this is also a sufficient condition for point to be indeed maxima or minima. And this is exactly what is the motivation of our subsequent lectures, that to develop a solid mathematical grounding in concepts of optimization, specifically engineering optimization, so that whenever we arrive at certain solution, we just don't stop there and do an end-to-end analysis that the answer that I have really found is indeed minima when I am asked to find minima, or maxima when I am asked to find maxima, and not vice versa, because in engineering systems that particular result, if you invert the positions of maxima with minima and vice versa, is going to have catastrophic outcomes, because task that was assigned is to minimize the height. You checked for the necessary conditions and ended up concluding without looking for sufficiency, and perhaps came up with the solution that is on other side of the problem, and that may end up resulting in much higher costs just because of the incomplete mathematics that was conducted. And that is exactly what we are going to discuss in this particular module, that is how to write equations, maths and do operations on various optimization problems. So, the first case that we are going to discuss is the case of univariate unconstrained optimization problem. So, there are two technical words that I would emphasize, one is unconstrained and one is univariate. By now optimization is already clear to us that we have to find the most efficient solution for certain mathematical equations that are given to us, to keep it very simple. So, for a univariate problem, I can list this particular problem mathematically is minimize f of x, and objective is to find that value of x that achieves this for us, where x belongs to real domain. One very simple example, f of x is equal to x square. Now, if you put x equal to 0, you would already know that in this case f of x is going to be 0. So, this x star in this case that gives minimum value to this particular function is what we call as arg min, or that particular value of argument that minimizes the function of interest, which in this case is f x, is called as arg min. So, sometimes you would encounter this particular word minimize, and in the foot written minimize min arg min, or sometimes just arg min x. That means that we have to find the minimum value of this particular function as well as that value of argument that at which this particular function would take that minimum value. Now, here you can clearly see that if you increase x in either direction from 0, I should not say increase, but x can also be minus 1 or x can be 1, you would see that f x will increase in either direction, and this is a classic equation of parabola that we have seen so many times in various contexts, and we know that indeed that this particular value is minima of this particular function, and this indeed is 0. So, for univariate problems we can always plot the graph, clearly see whether it is indeed minima or maxima without worrying about sufficiency condition. But again the moment we go from 1D to 2D to 3D or n dimensional problems, this visualization would not apply, and that is why we also need the sufficiency checks and hence the unconstrained optimization problem for multivariate would be stated differently. But before we go there, let us also briefly talk about constraint optimization problems. We will have dedicated lecture on the concept of constrained optimization problem, but this is just to tell you that this is the beginning of the optimization setup even for univariate and not the end, because there are multiple cases that we may have to discuss. So, in case of constrained optimization problem, so again we will state the objective function as is, that minimize x belongs to R, f of x. You may have to understand that your objective function is your desire. It has nothing to do with what resources are available, what constraints are there. So, for both constrained optimization problem and unconstrained optimization problem, your objective function would be same. So, for example, everybody would like to earn lot of money and become rich. If not everybody, most of the people would like to have that particular aspiration. So, that is the objective function, it is unconstrained. However, then real world constraints would come into picture, how much you can earn, what is your qualification, or what are you good at, and so on and so forth. And this is where these constraints become sort of brakes on your objective function, that your objective function now cannot have a free run, that if it is a maximization problem, I will go and take the value of infinity, if it is a minimization problem, I will take value of minus infinity. That choice is now curtailed by these constraints. These constraints could be of cost, could be of resources, could be around feasibility, that x cannot be a negative value. You are working on a minimization problem and somebody gives you a constraint that hey, everything is fine, but I will not accept a negative solution to particular x. So, then there is a clear cutoff that if you have a function like let us say f x is equal to x cube and you have to minimize that, you get very happy that I will put x equal to minus infinity and I will get answer as minus infinity. However, now a constraint is given to you that you know x has to be greater than equal to 0. So, now the minus infinity discussions are out of window, because you cannot have x less than equal to 0. So, in this case it is a very simple problem, you would know that the minimum value would indeed be at x equal to 0. So, I need not worry about that. However, these feasibility regions would become very important eventually when we will talk about linear programming problems or even nonlinear programming problems with constraints involved. And what these constraints do is that they shrink the feasibility region. So, shrink the feasibility region means that x has to belong to R, also it has to meet another condition that g of x should also be less than equal to 0. And if this is violated, then your solution no longer applies to the problem that has been given to us for analysis. So far you might have realized that you know all these discussions around univariates we have already learnt in high school, senior secondary school, what is a big deal about all these things. But the reason is that without having absolute clarity on what to do with univariate functions, learning multivariate functions would be immensely difficult. So, we wanted to gradually go along the curve of learning, but now I think we should pay more attention to how to derive these necessary and sufficient conditions, and then how to apply it to multivariates with certain adaptations. So, again I will not spend much time on this. That necessary condition is that first order derivative should be equal to 0, and sufficiency condition says that if we are looking for local minimum, I will come to the word local and global later on when I talk about convex functions, but when I say the word local, I am talking about whether a particular point in comparison to its neighbors is it minimum or maximum, and this may or may not be global minimum depending upon the shape of your function. But if you are looking for local minimum, you might have also learned that if you take double derivative and if it is greater than 0, that point indeed corresponds to local minimum, and vice versa, that is if second order derivative is less than 0, that point corresponds to local maximum. And one question that may arise, that what happens if the first derivative is 0 and so is the second derivative, so is the third derivative, then what happens? Then in that case we would say that if we stop at first and second and all of these are 0, then this point is mere an inflection point. It is neither maximum or local minimum. One example, a textbook example for such curves are like this. That is, if you look at this particular point of interest that I am just marking in red, you would indeed see that f dash x at this particular point is equal to 0, because slope is 0, as at this point curve is parallel to x axis. However, if you go slightly positive h, you would have a value higher than f of x dash. That means this point is not maximum. Why? Because the point on its right side neighbor has a larger value in comparison to this point. So, we cannot say that this is a maximum, and that is again where the word local comes into picture, that even it is in vicinity, even at a small distance h on right side, this particular curve has a value greater than the point of interest. Similarly, if you go minus h, you would see a value lower than the value at point x naught. So, on one side you have value less than that, on one other side, that is right side, you have value higher than that. So, this point is neither maximum or minimum, despite the fact that it meets the necessary condition that slope is equal to 0, and that is why checking for sufficiency becomes important, as I emphasized earlier as well. So, again a quick mathematical recap, that why this first order has to be 0 for a point to be local minimum or maximum. So, let us look into that. So, if we have any function f of x and if we want to expand it around any small value h, any perturbation on either side, this h could be positive, this h could be negative, we can write expansion of f of x plus h as f x plus h times f dash x plus h square into 1 by 2 f double dash x plus all other terms of h cube and higher, because this is an infinite series and it will continue with more orders coming into picture and so on. So, now let us look into these necessary and sufficient conditions to really ensure that the point that we have found is a local minimum or local maximum. Again, we are using this word local in the context that whether that particular value is the lowest in its vicinity or the highest in its vicinity, and we are not necessarily talking about the global optimal. We will talk about this local versus global distinction when we talk about convex functions in more detail, but right now our emphasis is on this first order and second order as necessary and sufficient conditions to establish that whether point is indeed minima or maxima. So, we have already learned that given a function, we will always take first derivative and we will get answer as 0, then we will say that this is our point of interest where we would be finding answer whether this point is maxima or minima. However, even if you meet this particular condition, that is your first order derivative is equal to 0, that does not necessarily guarantee that a particular point is going to be minima or maxima. And one good example of this particular type of function is function that would have some shape like this. If I identify a point here, let us say that this is x star, and at this x star I would have the slope, if this function has a relation functional form as f(x), at x star I can have the slope equal to 0, but if I see here, if I go slightly on the right and I will use the notation of plus h, I would see a value which is at f of x star plus h, value is greater than f of x star, and if I go on the value of minus h, what I would see is that f star x minus h is less than f of x star. Now, this equation takes away the right of x star being called as local maxima, and the second equation takes away the right of x star being called as local minima, because in its vicinity one point has a higher value, another point has a lower value. So, this particular point loses its claim, and this is a classic example of what we call as an inflection point, that despite the first order condition being met, your point is still not being is being qualified to be called as local maxima or minima. So, if I have the sign of second order derivative or an even order derivative existing, then I can guarantee that if f double dash x naught is greater than 0, it is local minimum, and if f double dash x naught is less than 0, it is local maximum. However, in certain cases we may have situations like this, where first order derivative is equal to 0, but second order derivative and subsequent even order derivatives also vanish and become equal to 0, then these points would be part of the families of points what we call as inflection points. Since we would be typically dealing with those points where we end up with having these slopes equal to 0, and then we will keep on going to check the sign of these higher order derivatives to really classify whether the critical point is indeed maxima or minima. It will become more clearer as we do two very quick derivations. So, if I look into the first derivation about the necessary condition, I can take a function f of x plus h and expand it around x. I can say that f of x plus h is f of x, h times f dash x plus h square into 1 by 2 f double dash x plus all other terms that are having h cube h4, because this is going to be infinite series all the way to infinite terms. But if my h is very small, the higher order terms can be grouped together and typically mentioned as the order effect of higher order terms. Now, if you recall that when we do the derivation or differentiation by first principle, we say that f dash x is f of x plus h minus f x divided by h. If the point of interest, let us say that x star is the point which I am searching for minima. If x star is indeed the point at which f of x has minimum value, then I can say that f of x should be less than equal to f of x plus h. Also, f of x should also be less than f of x minus h. If both of these particular conditions are met, only then I can say that this particular point is minimum. Now, if we focus on this particular condition and these two equations, that this is invariant of side of h, does not matter if h is positive or h is negative, in both cases you have f of x star less than f of x star plus h, f of x star minus h. I am writing x star because this is the point of interest for me, because that is where I am suspecting my local minima is there. Now, for this particular point to be minimum, what I can say about numerator? I can say about numerator is that f of x plus h minus f of x would be greater than equal to 0 for all h greater than equal to 0 if f of x is indeed minimum. Similarly, f dash x is less than equal to 0 for h less than equal to 0 if I am talking about these two conditions as well. Of course, h cannot be equal to 0. So, I would stay away from h being exactly equal to 0. Now, for both of these conditions to be satisfied simultaneously, there is only one and one way that f of x can be greater than equal to 0 as well as f dash x less than equal to 0 is that to be invariant from the sign of h, f dash x can only be equal to 0 for this particular point to be indeed minima. And same argument applies when we talk about the necessary condition for maxima. Also, remember that if I am given a question that minimize f of x, this is as good as saying that maximize minus f of x, right. So, we can always use this argument of maximization versus minimization interchangeably because the negative sign would also change the sign of min to max and so on. So, if this is necessary condition, let us look into the sufficiency condition that we have been talking about f double dash x and so on. That can we also look into this in the context of Taylor expansion. One thing we have ensured is that we cannot have the signs in the neighborhood flip just because of h. If point is minimum, it should have lesser values in comparison to right neighbor as well as left neighbor. So, it should not depend upon sign of h. So, similarly, when I write sufficiency condition using Taylor expansion, I can say that f of x plus h as f of x plus h times f dash x, h square half f double dash x and some higher order terms. I can again for mathematical convenience, I can club all these as OH cube. We have already established the necessary condition that at x naught f dash x should be equal to 0. So, we are only left with this particular term, that is f of x naught plus h is equal to 1 by 2 f double dash x naught h square, and I am also removing the effect of this particular term, assuming that h is so small that higher orders of h would can be approximated by 0. Now, if we focus on this particular problem, if we see this particular f dash x naught greater than 0, only then and of course, there is one more term of f of x naught, only term that would be put to 0 is the first order derivative and this term still exists. So, we are essentially dealing with the value of function at point of interest plus the second order derivative, because first order derivative has already vanished by the necessary condition. So, if x naught has to be minima, then what we can say is that f of x naught plus h minus f of x naught, first of all just bringing this term here before we do that analysis, I can write this as f of x naught plus h minus f of x naught as 1 by 2 f double dash x naught into h square. So, h square irrespective of sign of h, this is always going to be a positive quantity, 1 by 2 is not going to bother us. So, we are only left with the checking the sign of f double dash x. Now, if f double dash x is greater than 0, what happens is that if this is greater than 0, that means f of x plus h becomes larger than f of x. Again, f of x at that particular point x naught. So, if it is greater, that means this point is minima in comparison to f of x plus h. So, minima is happening when your f dash x takes value greater than 0 or is positive, and that is exactly what we have been thinking about this all our lives in terms of curvatures and so on. But if you just look into the Taylor expansion, we also end up with a better mathematical justification that why indeed second order or even derivatives should be seen. Now, we can also argue that what happens, that let us say that first derivative is 0, then second derivative is also 0, but third derivative happens to be non-zero. Then again, if you have value of h to be positive, h cube will be positive. If you have h to be negative, h cube would take a negative value. So, on one side you have a value greater than f of x naught, on another side you have value lesser than f of x naught, and again that would be called an inflection point instead of the local maxima or local minima. Again, one important emphasis I would like to put here is that that inflection point does not necessarily mean that the first derivative has to vanish. However, given that first derivative has vanished, how the second, third, fourth derivative should look like, so that we can really call that particular point to be maxima or minima. So, given that necessary condition is met, how to check for sufficiency condition. So, if f dash x equal to 0, then we keep on going to higher order terms. If we find the first even order term to be 0 to be greater than 0, then we would conclude that this point is minima, and if the value is less than 0, we would conclude that particular point to be maxima, again originating from this particular Taylor expansion and separation of terms, and applying the same reasoning that f of x naught has to be lesser than f of x plus h irrespective of sign of h, and hence this becomes much more solid grounding in our understanding that why sufficiency is important once the necessary conditions are met in the field of engineering optimization. I have written the same example in bit more mathematical form, that you can go all the way to higher order terms, and if you focus on this, I can write the last term in some form of n if I ignore the effects of higher order terms. So, I cannot have this function to be dependent on sign of h to establish whether it is local minima or maxima, and that can only happen when h is even, or when first non-zero, when first derivative I should say takes a non-zero value, at that time this n needs to be even to guarantee that that point is indeed minimum or maximum. So, let us do one very quick example that how we would find the local maxima and minima of this particular function. I have deliberately chosen this particular equation because this would have lot of point of interest where slope is actually equal to 0, but some of them would indeed be local maxima, some of them would be local minima, and some of them would be mere inflection points that we will establish at part of this particular example. So, f of x is given to us as 12x to the power 5 minus 45x 4 plus 40x cube plus 5 and so on. So, first, what we will do, we will take the derivative with respect to x. This comes out to be 60 x 4 minus 3x cube plus 2x square. You can do this particular math by taking certain terms common. We can write this as 60 x square, x minus 1, x minus 2. Now, for f dash x to be 0, I can clearly see that this particular equation has 3 roots. One is x equal to 0, one is x equal to 1 and another is x equal to 2. At x equal to 1, if I check sign of f double dash x, this comes out to be minus 60. I will leave that particular part to you, that just take this derivative once more and this value should come out to be minus 60. Now, you clearly see that f dash x was equal to 0, f double dash x is less than 0. So, this point indeed has to be local maxima. When we talk about x equal to 2, f double dash x comes out to be 240 greater than 0. It is guaranteed to be local minima. I am using the word guaranteed very confidently because both necessary and sufficient conditions are met. And in mathematics, guarantee is a big word, but here by looking at the sign of second order derivative, I can confidently with 100% certainty make that particular statement, because that is what the fundamental derivation would take me to, that you can be double assured that as and when you encounter first non-zero derivative which happens to be of even order, that would indeed guarantee whether that point is minima or maxima. Similarly, when we look at x equal to 0, I do get f double dash x to be 0 and this would be a mere inflection point. So, out of these 3 solutions, I have identified my local maxima, local minima and inflection point based on what we have learned. Now, taking it to more complex case where multivariate optimization is involved, but without constraint, instead of dealing with one single value of one single variable x, I will deal with vectors of x. This may deserve some attention because here specifically when we will go to higher order derivatives, math would be bit different. So, please pay attention to this particular concept if you have not already learned this in your mathematics classes. So, instead of dealing with just x, I would now be minimizing function of x1, x2, x3, x4 and so on. One very simple example of such function is that function in x and y, let us say x square y. Another function in multivariable is an equation of circle x square plus y square and so on. Now, you can bring in more variables. What we can do with 2 variables, we can also do with more than 2 variables, of course, with added computational or mathematical complexity, but whatever we would learn for 2 variables would generalize to n number of variables and so on. So, in general form, what we are looking for, we are mapping R n to R because output of this particular function is just going to be one value, right. So, from n dimensional space we are moving to one dimensional space or just a real number mapping of this particular function from R n to R, where our function is f of x1, x2, x3 and we have to find whether that particular value is maximum, minimum and so on. Again we will go by the fundamentals, what we did for univariate we will also do for multivariate. In similar fashion we expanded univariate f of x plus h, we can also expand multivariate of f of x plus h, but understand that now h is also a vector and x is also a vector, where h is a small perturbation around each x. So, x1 plus h1, x2 plus h2, x3 plus h3. So, my h vector in this case becomes h1, h2, h3, my x vector becomes x1, x2, x3, and my function in this case becomes some function of x1, x2, x3, and in compact notation I am writing this as a bold x. Wherever I will use bold x or bold y, I am essentially talking about the vector and not a single variable x or y and so on. So, please remember this particular distinction going forward. So, wherever bold words are written, those are vectors of x or h as applicable. So, what we did, we will apply very similar understanding that f of x naught plus h is equal to f of x naught plus instead of differentiation we will use gradient of f of x naught again multiplied by h plus half h t h. Remember, it was h square f double dash x when we were talking about the case of univariates. Here 1 by 2 remains same, h transpose h is equivalent to h square, and instead of taking the second derivative we would be taking the double gradient of f of x naught plus all other higher order terms encapsulated here. You can go all the way, but again whatever we can do for first few terms that would generalize as you keep on searching for first non-zero term. Now, this particular term here del square f of x, I should exclude h out of this, has a very special name and place in multivariate optimization, and this is called as Hessian matrix, and this is very closely related to Jacobian matrix that you might be familiar about, but for us it is its equivalence comes from the second order derivative in univariate, but here it would take the form of a Hessian matrix that we are going to talk about in further detail, and as we already discussed, h is the small perturbation vector. So, if I talk about f of x naught, that is not a problem. At the point of interest, give me the values of x1, x2, x3 and so on, I will plug it in my particular function and get the value of f x, and this is indeed f of x naught. But what about this del of f x naught? What I would do, I will differentiate each term with respect to x1, x2 and xn, and output would also be a vector. So, that is going to be my del of f x naught, and h again is a vector of small disturbances or displacements that we have given, and I have ensured to use transpose here so that multiplication compatibility is maintained, right, because if I have to multiply two vectors I have to ensure that their inner dimensions agree, and that is what this transpose is taking care of. So, what looks mathematically very intimidating is nothing but an extension of what we learned in univariates to multivariates, but now in vectorized notation. So, this also gives the directional derivative of f in the direction of h, right, because whatever we applied to the calculation of derivative, because if you take this here and divide it by h, this again becomes the derivation or differentiation by first principle. Same argument also applies to multivariates. This particular term is bit interesting and complex, so please pay attention, and this is where some deviation happens from univariate to multivariate optimization, is that in second term we have to look into del square f of x naught h, and this del square f of x naught is double differentiation with respect to x1, double differentiation with respect to x2 up to n number of variables along the diagonal, and this is a symmetric matrix. So, what we will do? We will do del square f del x1 del x2, del square f del x1 del xn, and similarly del square f del x2 del xn and so on, and put all those gradients of first differentiations into this particular matrix, and the resultant matrix that we get has a very special name, what we call as Hessian matrix. And what we were doing with sign of second derivatives, we will now do it with Hessian matrices. So, again there is one more term, order h cube. Sometimes students get confused. So, I have just qualified it that these are all the terms involving h cube h4. So, I have not stopped the expansion, I have just lumped everything together to keep the computational complexity at bay. What I did for univariates, the similar mathematical operation I have applied here also. So, all the terms of order h cube, and this is the remainder of order h cube, and they will just keep on vanishing and hence get smaller. So, again coming to necessary conditions for multivariate optimization, nothing changes here. What we were having, f of x naught equal to 0, we can write analogously that del of f of x naught equal to 0. That means del of f of x1 equal to 0, del of f of x with respect to x2 equal to 0. So, their partial derivatives of function f with respect to individual variables is equal to 0, and that gives us the necessary condition along the similar lines. When we talk about the sufficiency condition, we have to look into this Hessian matrix that we already spoke about, and look into that whether this Hessian matrix is positive or Hessian matrix is negative. I have put this in quotes because how can I say that a matrix is positive or negative? That requires bit of understanding that we are going to do now, because if all values are positive, does it make a matrix positive? If all values are negative, does it make the value of the matrix negative? Answer is not necessary, right? Signs of elements have nothing to do with sign of the matrix, but of course the signs of values would impact the properties of a matrix, and these properties is that what we are going to look into to establish whether matrix is positive or negative. So, what we do here is that we construct that particular Hessian matrix, and Hessian matrix is also closely related to Jacobian matrix, as I already mentioned that Jacobian matrix is the first order derivative of f partial derivatives with respect to x1, x2 and so on arranged in particular matrix, and if you take the derivative of Jacobian itself, you end up with the Hessian matrix. So, sometimes book use the notation J to represent the Hessian matrix, but I really wanted to make that particular distinction that do not confuse that J for Jacobian matrix, because Jacobian matrix is not necessarily equal to Hessian matrix, because the order of derivatives change from Jacobian to Hessian. So, why Hessian is important? Because first order information only identifies critical points, second order information is essentially to classify those points as maximum, minimum or inflection points. Again a quick recap, what we did is that we expanded that, first term already vanished. So, everything lies on this particular term. If you see here H transpose H is present, which is talking about H square. So, this is not going to create a problem as long as we are on even orders of H. So, H square, H4, H6, these are not going to create problems. So, the contention falls on del square f of x naught, and for which we are going to search for the sign, as this behavior of f x near x naught is determined by sign of this particular term. So, one way to check whether a matrix is quote unquote positive or negative is to check whether it is positive definite, negative definite or indefinite. And when we talk about this positive definiteness, we are essentially talking about its eigen values. So, if all eigen values of matrix are positive, then we can say that it is positive definite matrix. Similarly, if I am not saying one, I am saying all, that word is important. So, sometimes students think, oh, I got one eigenvalue as 2, so I should stop my search and say that eigenvalue is positive, so it is going to be a positive definite matrix. That is incorrect. You have to look into sign of all eigenvalues. If all eigenvalues are greater than 0, it is positive definite. I am also not saying equal to 0, I am saying greater than 0. If all eigenvalues are less than 0, it is negative definite, and if you have some values as positive, some values are negative. You cannot comment whether it is positive definite or positive or negative definite and so on, and this is essentially what I meant by the positive matrix and negative matrix. So, putting it together, Hessian matrix is a square matrix. Hessian matrix is a square matrix, so we can always find eigenvalues, we can check the sign of eigenvalues, we can say whether it is positive or negative, and we learned that if second order derivative is greater than 0, given that first derivative has vanished, that means that particular point is local minima, and vice versa. That means if the Hessian matrix is negative, given that first order derivative has vanished, that particular point is going to be local maxima, because H naught H is not going to trouble us with the sign. So, all prerogative falls on this particular H. One question that should arise at this particular point is that why eigenvalues? Why not some other way to actually quantify whether this matrix is indeed positive or negative? Because eigenvalues tell us how much a matrix stretches or compresses a vector in a given direction. So, if all eigenvalues are positive, it means that H stretches vectors in all directions, confirming the upward curvature. However, if one eigenvalue is positive and the corresponding eigenvector would be sort of compressing it inside, whereas the positive value would be pulling it outside. So, if I plot this in 2 dimension, we will have an exactly similar behavior that we were talking about an earlier curve, something like this, that here at point of inflection you may have one value stretching, one value compressing, as a result of which one value being positive and another being negative does not give us the guarantee whether the point is indeed minima or maxima. So, if I show you this particular example where we see these 3 plots, in this case eigenvalues are computed to be lambda 1 equal to 2, lambda 2 equal to 2 at the point x star y star equal to 0. I did this particular calculation for you, but in this particular case the eigenvalues for this particular curve comes out to be 2, 2. So, both the eigenvalues are positive. If both the eigenvalues are positive, what does that mean? That means that this point at this point we also checked and that the gradient of f is equal to 0. Gradient of f equal to 0, both eigenvalues are positive. At this point it is guaranteed that this particular point is local minima, and it is also evident from the plot that we have generated. If we look into another instance of this, we get both eigenvalues as -2 negative, and as a result of which we can see that this particular point corresponds to local maxima. In this case it is also global maxima, by the way, because it is a convex function that I am going to eventually talk about. However, if you see the third case, this point has one eigenvalues as +2, another eigenvalue as -2, and it is very clearly visible that it looks like a horse saddle. If you see a horse, a seat on top of it, it would look something like that. So, that point neither corresponds to maxima nor corresponds to minima, and also eigenvalues are also telling that despite gradient of f being equal to 0 in all directions, the eigenvalues do not have a consistent sign of being positive or negative. So, the only comment I can make here is that this is an inflection point, but not necessarily a point which is a maxima or minima, as we can also see from this particular graphic. Now, this brings us to the discussion that I have been using word local and global. So, what is the distinction? So, distinction is that when I talk about local maximum or minimum, it is a point where function is at maximum or minimum in a small neighborhood. So, I was using this notation of +h, -h, where h tends to 0, because if h tends to 0, and that is how I was doing the Taylor expansion around that particular point and deriving all the results around that. So, I was indeed talking about local maxima or minima in all the derivations that I have done so far. However, when we talk about global maxima, we talk about the overall height or the lowest point of the function over its entire domain. So, if function is defined from minus infinity to infinity, that point that is local minima, if that also happens to be global minima or the minimum value throughout the domain, then we can say that that point is indeed a global minima. One example that we are used to see are curves like this. In this, if you are searching for a minima from all the maths that we have done, you will stumble upon this point, and you would indeed see that even if you go from minus infinity to infinity, there is no point lower than this point. So, although your search was using local methods around that particular location, you would not have any other point lower than this particular point. So, in this case, this local minima indeed is global minima also, and this happens with a function that have a very distinct name and used widely in data sciences, machine learning, optimization, what we call as the convex functions. So, if our function is convex or concave, right, again as I said, if you multiply a maximization by a negative sign, it becomes a minimization problem. You take a convex function, multiply it with negative sign, not the values, but the function itself, it would invert itself, and convex and concave again are used interchangeably. So, whatever math we do with one also applies to other with the sign change. But if our function is indeed a convex or concave, whatever local optima we get is guaranteed to be global optimal as well, and that is what we do, is that we check for convexity of any given function. So, one quick way to check for convexity of a particular function is that if its second derivative is greater than equal to 0 for all values of x in entire domain, then that point indeed is that particular function is indeed a convex function. Another way to think about convex function is using our simple parabola example. Let us say that these are 2 points x1 and x2. I will draw a straight line joining these points. What you see here is that all the points that lie on this particular line, other than these 2 secant points, they are always above the function. This is the function. So, all the points are always above that particular function. So, if I can draw, and I can draw any line like this, by the way, I can draw any secant, and all these secants would always have values above this. Now, let me change a function. If I change a function and I make it something like this, right. Now, if I draw a line, let us say between these 2 points, something like this, I would see that here in this zone, this line is above the function, in second zone this line is below the function, and in third piece it is again above the function. So, that means that this is a different minima, this is a different minima, and this is a different maxima. So, they may be very happy that I am maxima, and they may be relatively sad that we are minima, but all of these are local minima in comparison to their neighborhoods. It may happen that this particular point is happy or sad based on what is the objective here, that I am the minima, but there is another point for the same function outside this particular neighborhood which has even lower value. So, globally this happens to be a global minima, and this point happens to be local minima, and this function ceases to be a convex function or concave function if I multiply it by negative sign, just because its local minimum does not coincide with global minimum, or it does not have a unique minimum in its entire domain that we can call as a global minimum or maximum unequivocally, as a result of which we take away the right of this particular function to be called as convex. So, what I said, I can always write a math for that, that value of function at any point along the line, equation of line is lambda x1 plus 1 minus lambda x2, where lambda can take value between 0 and 1 both included, how far you are from x1 and x2. It has to be always less than the lambda f of x1 plus 1 minus lambda f of x2, and that would ensure that the function lies below or on the secant line between x1 and x2, including the boundary conditions included. So, there is some qualification. We can have a function which we can simply say convex, and another function which is strictly convex. So, y equal to x square, it is a strictly convex function, that other than these 2 points from where line has originated and terminating, all the points are less than all the values of the function are less than the values on the line. So, it is strictly doing that. However, when I talk about a straight line, I can always draw another color line on top of that, whose values are less than equal to the original line that I was there. So, line is also a convex function or concave function, howsoever you see that, but not strictly convex nor strictly concave. But all the values would be satisfied with an equal sign when I talk about the lines. So, this and what applies to lines also extends to hyperplanes, because lines in higher dimension would become hyperplanes. So, this guarantee of convexity for lines and hyperplanes would give me an armor to deal with linear programming problems, because whatever optimal I would find in those particular cases would be guaranteed to be local maximum or local minimum, and by virtue of guaranteed convexity of straight lines would also be global maximum or global minimum. So, if I can express my objective function and constraints in linear form, and whatever optimality I derive for those particular equations, that is guaranteed to be global maximum or global minimum. And this was the story that goes back to the World War, when one of the engineer Danzig actually noticed that and came up with this entire new paradigm of linear programming problems, where there is no worry at all to get stuck in local minimas or maximas if your objective functions and constraints are indeed expressed as the linearized systems of equation. Then there is no worry to get stuck in local minima or maxima, but that is what we will discuss when we go to linear programming problems. But I think that was a good time to talk about that, why this convexity is so important when we talk about real time resource allocation. Again, a neat representation of the curve that I have been talking about. So, if you focus from minus 1.5 to 1.5, if I draw a line between these 2 points, all the values are above this particular curve which is drawn in blue. This indeed is a convex function. Y is equal to x square is a good way to remember that where line would be there, and so on. Again, we can do lot of tests on this. What we have done, what we were checking for one point, we can check it for entire domain. Similarly, Hessian matrix should be positive semi-definite throughout the domain. I use the word semi-definite because semi-definite allows to be 0. When I talk about positive definite, it has to be greater than 0. Greater than equal to 0 would give me positive semi-definite. If I have to drop the word semi, I have to also drop the 0 eigenvalues and focus on greater than 0 eigenvalues. Fxy is convex. When I am talking about semi-definite, I have also dropped the word strictly. I am just saying convex, not strictly convex. And again, one test that we learned is that secant line test, that all these particular values should be functional value should be below that particular line. Now that we have learned all this, we will do one example on how this concept of optimization, multivariate optimization can be designed or used to focus on a real world engineering problem, that is to design a levee. So, let us look into an example of putting these concepts of multivariate optimization to use in the context of infrastructure systems. In this problem, we will try to design a levee. So, if you are not familiar what a levee is typically a high embankment provided on either side of water carrying structure, for example river or canal, that would raise the capacity of that particular water body, so that when there is a flood like situation, that water body like river or canal can hold more water in it. However, you can imagine that if you have to design a levee along length of the river or for a particular stretch running through the city, it would entail money. So, you would want to optimize the dimensions of that particular levee so that the costs are minimized. However, these levees are also structural elements. So, you have to give them dimensions appropriately so that the structural integrity or stability is not compromised. So, here is a problem where we are said that an engineering firm is designing a levee along a river bank to prevent flooding. The levee must have a trapezoidal cross section. So, if I draw the sketch, it should have a trapezoidal section like this, and we can expect water to be present somewhere here. It has some top width T, it has some base width which is equal to B, and height is fixed for us which is equal to 3 meter. So, we will not optimize for height, but we will optimize for top width and bottom width. Now, it is also given that levee extends for the length of 5000 meters, or we are designing it for 5 kilometers, perhaps covering entire city. Now, various constraints are given to us. Remember, so far we have only learned unconstrained programming, but an engineering problem may have certain constraints specified. So, we will see this example that based on what we have already learned, how we can still solve this particular problem without using any additional mathematics. In subsequent lectures, I will discuss methods to explicitly account for these constraints in your mathematical formulation, but right now we will just be aware that these constraints exist, but without changing our mathematical framework, we will still try to answer the key question that would be asked to us. So, it is said that this T should be greater than 1 meter and base should be greater than 4 meter. Now, as I mentioned that if the dimensions of your levee increase, the total annual cost for building and maintaining the levee is also going to increase. So, it is 50 times the volume, it is 200 times the base area and some other parameter which depends on the length and the top width of that particular levee. Now, if you see that there is a volume term involved, volume is going to be area multiplied by length, and we already mentioned that this particular levee is going to have a shape of trapezoid. So, trapezoid would have an area of base plus top divided by 2 into height, and width of the base is given to be B and total length is L. So, SB, that is base area, would come out to be B into L. What we know in this particular question? We know L, we know H because this is fixed, but we do not know B and we do not know T. However, we have some constraints around B and T that we will try to see how to incorporate into our problem. So, what is the problem at hand? Problem is that determine those values of B and T that minimize the total annual cost. We are also asked to verify the necessary and sufficient conditions for a minimum are satisfied by computing the gradient and the Hessian matrix. Let us see how far we can go into this particular problem, if at all it is possible to apply all the math to a real problem. So, here is how a typical levee looks like. If you have not seen levee, that if you see that there is a river here, there is a road here, and this particular stretch is artificially raised, and this is what we mention as levy, and it does cost money because we have to ensure that the water does not seep through to the highways through that, and also we have to make sure that the vegetation cover is maintained to certain optimal. Regular maintenance would happen so that there are no gully formation into these particular levees, otherwise they may result in entire slope failure and the purpose may be defeated. So, if this is clear, let us start putting the solution together. First of all, what I will do, I will write the cost function. So, what is given to us, that cost function as function of B and T is equal to 50 V B times T plus 200 time SB plus 1000 L by T. Now, V is given to us as A cross L and area is given to us as B plus T divided by 2 into H, and H is given to us as 3. So, this reduces to B plus T divided by 2 into 3, and volume of this levy would come out to be A, which is function of B into T multiply by length of the levy, which is again given to us as 5000, and base area would be simply B multiplied by length of the levy, which is 5000, and we have substituted all the values here. So, now I can put all these components of A, V and S into my equation 1 that I am currently highlighting and numbering as 1, and get this in a form of 750000 B plus T divided by 2 plus 1 million B plus 1000 into 5000 divided by T. Now, this is the cost function which is bivariate. So, whatever we do here would also apply to multivariate conditions. In this case, it is restricted to B and T. Even if it is function of H, I will also have one H term which is not needed here and so on. But the fundamental remains same, that to satisfy to meet the necessary conditions, what I will do, I will take differentiation of this with respect to T and equate to 0. I will take partial differentiation of cost function with respect to B and equate to 0. When I take the partial differentiation of C with respect to T, I get an equation of form 375000 minus 5000 into 1000, which was product of the constant multiplied by the length as we saw in previous equation, and when I equate it to 0, I get value of top width in this case as 3.65 meter. I am not going to solve this for you, you can check it for yourself as part of the homework, but we get T is equal to 3.65 meter. However, an interesting thing would happen when we differentiate this expression, the expression that we derived earlier with respect to B, and we will only get a term which would give us the value when we equate it to 0, this would come out to be some constant which cannot be solved for B. Now, what does that mean is that this necessary condition is satisfied when we partially differentiated with respect to T. However, partial differentiation with respect to B does not give us any clear answer. Now, if necessary condition is not met, there is no point in checking for sufficiency condition. So, we have to practically go back to our question or problem and identify what is the best decision we can take even if we hit this mathematical infeasibility purely from mathematical side. So, one thing is clear that there is no doubt about H, there is no confusion about T, but B is not giving us clear answer. So, that also means that it is not possible to optimize the given mathematical function in B. So, what we will do, we will go with the constraints where we said that the B should be greater than 4 meter, and the boundary condition should give us that particular answer, that to ensure structural stability, if we provide B is equal to 4 meter, that is not violating any constraint. Although that is not necessarily minimizing the cost here, but going by the necessary condition, this is the best decision that we can take to provide a particular B. Also, we come out with certain top width is equal to 3.65 meter. There was a constraint that top width should be greater than 1 meter. We have already met that particular constraint. So, this also holds true for the decision that we are taking. So, we have all decision variables in place now, that h is equal to 3 meter, t is equal to 3.6 meter, and give B is equal to 4 meter. With these dimensions, you can go ahead and design the levee, and the cost associated indeed is going to be minimum under the information that has been provided. So, this example clearly tells us that wherever possible, we should stick to our fundamental derivation, fundamental understanding of necessary and sufficient conditions, but in real world we will often hit the points where the necessary conditions are not being met, but still we have to take an informed decision, account for the information that has been given to us, and in such cases these constraints does help us take these particular decisions. Now, this is a simple problem, I would say, where constraints were simple values. However, in other situations we can have these constraints specified in form of equations, multivariate equations. The objective function is also multivariate. These constraints can be equality constraints, that is, they have to be exactly equal to certain value. For example, here we can say that h equal to 3 meter, it's a hard constraint that it has to be met. Although h did not participate in our decision making of cost, because we already fixed it that particular value. However, in many cases these hard constraints may be present in functional form rather than just the explicit value like h equal to 3 given to us. So, even in those situations we have to take the decision, we have to account for all these constraints, both equality constraints and inequality constraints, which is going to be a very important part of our discussions as we go forward. So, in next lecture we are going to touch upon these concepts of multivariate optimization with equality constraints, and subsequently we will move on to multivariate optimization with inequality constraints.